Today we are going to study about quantum confinement and Brus equation. We know that when we are talking about nanomaterials, then there are two very prominent effects which we have to take into consideration. The first one is the quantum confinement effect, and the second one is the surface effect. So you see that when the size of a material reaches in the nanometer range, then because of quantum confinement, the energy band structure will change, and this we have discussed in the class. This is based upon the particle in a box model. So here, if the size of the material is large, then the energy band structure will be such that there will be continuum of states available, and if the size of the material is in the nanometer range, then the states will be discrete, and the band gap will increase, and no more continuum of states will no more be there. So we see that there are two effects: the band gap is increasing and the states are becoming discrete. So in this case we are talking about a semiconductor material and confinement of electron as well as hole. So we have drawn two wells here. So this is the first well is for the electron and the other well is for the hole, and we are talking about a semiconductor material. Also, because when incident photon is when a photon is incident on the material, then an electron hole pair will be formed in bulk material as well as in a nanomaterial. And we have discussed this in class that the exciton binding energy is very large in case of a nanomaterial as compared to a bulk material. And in bulk also you have excitons, but the binding energy is very small, but it increases if the temperature is decreased. While in nanomaterial, because the binding energy is very large, so it is greater than the thermal energy kT, and therefore you can find excitons even at room temperature in a nanomaterial. So because of this higher binding energy, so you'll have to take care of the Coulombic forces between electron and hole. So attractive forces between a positive charged particle and a negative charged particle. Okay, so just a little bit of revision of what we have done. So you see that if the particle is confined, the electron and hole are confined in their respective quantum wells, then the first energy level will shift from its ground state to its first state. I will not call it excited state. So the ground state will shift from here to here. So that is why the band gap will be now between these two states. So if you have to find out the energy of these, if the electron is present in these energy levels, it will be given by this relation, while for the hole it will be given by this relation. So because we are talking about a material in which electron is surrounded by ions, and so that is why we'll have to take we'll have to replace the free electron mass by effective mass of the electron and effective mass of the hole. So it means that this band gap in a nanomaterial will actually be a sum of the band gap of a bulk material plus the kinetic energy provided by confinement for the electron and kinetic energy provided by confinement for the hole. So this equation will turn out to be this, and we can replace 1 upon me star plus 1 upon mh star by its reduced mass. So this is the case when you have a cuboidal or particle in a box kind of a model, and the particle is cube. But if the particle is a spherical particle, then you can replace this length by diameter. So diameter will be radius upon 2. Therefore, you will get a factor of 2 here. So the optical transitions in quantum dots are usually, as we have discussed, they are associated with excitons. And therefore, this expression actually needs some rectification. So we'll have to add another term here, which will be the Coulombic term. Okay. So because of the Coulomb attraction, you'll have to add this binding energy of exciton, which will be the Coulomb force between electron and hole. So this equation is actually called the Brus equation. It's a very famous equation, and it will so this term actually is due to the confinement, and this term is because of the Coulombic force between electron and hole. So that is why we can actually separate the two terms, confinement and Coulombic terms, which we'll see how we can understand it. So another parameter which is very important in semiconductors is the Exciton-Bohr excitonic radius. So Bohr excitonic radius is given by this relation, and it can be written in terms of the Bohr radius. So you can check a hydrogen model, Bohr's model for hydrogen atom, and you'll find that the Bohr radius is given by A naught, which is actually 4 pi epsilon naught me into h bar square n square, and which is actually equal to 0.53 angstrom. So just give you a glimpse of how we did it initially for the Bohr's model. So we know that angular momentum is quantized in Bohr's model, so from here you can use this equation, and then you also know that a Coulombic force is given by the centripetal force. So from here you can find out velocity, put its value here, find the radius from there, and that will give you A naught. And in order to find the Exciton-Bohr radius, you just replace epsilon naught by epsilon naught epsilon r, and because the mass, we are not talking about a free about the only the mass of the electron, we're talking about the mass of electron and hole, so we'll have to take care of both. So here we are replacing me by mr star, reduced mass of electron and hole. Just multiply it with me mass of electron, and then try to incorporate Bohr radius. So this is how you will find this relation which we have written here. So it means that the Exciton-Bohr radius depends upon mass of the electron and the reduced mass of electron and hole, as well as the permittivity of the material. So in quantum dots, the separation between electron and hole is influenced by the size, because if the size will decrease, the electron and hole will be nearer, as compared to the size is large, then they will be at a larger distance. So you see that if the size of the material is larger, the distance between electron and hole will be smaller, and as you increase the size, the band structure will go from continuum to discrete, energy band gap will increase, and the distance between electron and hole will also decrease. So this radius, the distance between electron and hole in the bulk material, is actually known as Bohr excitonic radius, and this will give you this actually acts as a good measure of quantum confinement in quantum dots, and you'll see that in many publications they will be talking about this what kind of quantum confinement it is. So if the radius of the material is very large than Bohr excitonic radius, we say that there will be no confinement effects or slight confinement effects. But if it is very large, there will be no confinement effects. And if it is greater than excitonic radius, then you see that 1 upon r square will be less than 1 upon r. So it means that the confinement energy will be less as compared to the Coulombic attraction between electron and hole, and therefore this term will dominate as compared to the confinement term. So electron and hole will act as a pair because of this Coulomb attraction, and therefore we can talk about electron and hole together, and we can use Brus equation, and instead of reduced mass we'll use the excitonic mass, which is also in a way a reduced mass of electron and hole. Whereas a strong confinement occurs when the radius is very less than the Bohr excitonic radius. So if this is the situation, then 1 upon r square will be greater than 1 upon r. So it means that the confinement energy will be much greater than the Coulombic energy. So when confinement energy is very large, it means that the electron and hole will have a large amount of kinetic energy. So they are moving with a very large energy. So therefore the Coulombic attraction between the electron and hole will be, in comparison to confinement energy, it will be lesser. That is why the electron and hole will not be as bound as they are when the radius is of the order of the Bohr excitonic radius. and therefore they will have a higher amount of kinetic energies, and therefore we'll have to take them separately, and therefore the Brus equation will turn out to be this. Here we can also add Coulombic term, although it will have lesser magnitude, but still we cannot neglect it. But just for clarity's sake, I have just taken these two terms. So this is all we had to discuss about quantum confinement.